This video is going to be looking at the intermolecular forces that can be between molecules. This is part of Unit 2 of the Edexcel IAS chemistry course. So we're going to be looking at how the intermolecular forces are formed. So we have London forces, permanent dipole, and hydrogen bonds. We're also going to be looking in a little bit more detail with hydrogen bonding and also how we are able to then predict these hydrogen bonds if they are going to be present or not. And this will link into topic 7b, which is the physical properties, but you can find that content in a different video. So intermolecular forces are sometimes known as non-bonded forces. And these are the interactions that exist between molecules. So we're moving away from our covalent, ionic, and metallic bonding. Those are intramolecular forces. So intra means in molecules, whereas inter is between the molecules. These are typically weaker than our covalent and our polar covalent bonds. And there are three that we have to understand, and we have to be able to explain how they are formed and give examples of substances that would have these. So the first is called London forces, sometimes known as London dispersion forces. Second is dipole-dipole interactions, and that's focusing on permanent dipoles. And then we have hydrogen bonding. Now, sometimes you may see in textbooks or in websites, it says van der Waals forces. This is generally used as an umbrella term. So van der Waals forces cover all of these intermolecular forces, or sometimes they can be referring just to London forces. I would recommend avoiding the use of van der Waals forces because it is a bit of a general term. The terms that you should be using as part of the Edexcel course are the three terms here, because that is what is required in the specification. So let's start off by looking at the first one. So London forces are an intermolecular force that is going to exist within any substance that has an electron. So basically, London forces will exist in all substances. Now, we know that within an atom or a molecule, the electrons will move because they've got a specific area that they move within their orbital. Now, normally, the electrons should move in a nice uniform manner. So if I have my molecule or my atom, if I have my 4 electrons, when they move, theoretically, they should be evenly spaced. So we get a symmetrical movement. Now, in reality, this doesn't happen. In reality, what actually happens is the electrons become bunched up, a bit like that. So I've got this open space here, and we get this unsymmetrical movement. And when this electron density within the atom becomes unsymmetrical, we form a dipole. Now remember, a dipole is a separation of charge. So that means that we have a positive end or a negative end, and it could even be a delta positive or delta negative. And that's what happens in this particular instance. So we have our unsymmetrical electron density, and we form this dipole, and we call it an instantaneous dipole because it only exists for very short periods of time. So the instantaneous dipole will have a delta positive end and a delta negative end. So your electrons, when they are moving, are all gathered in this space. And because they are all gathered on the left-hand side, it causes the right-hand side to become the delta positive. Now, when this happens, and we get this dipole being formed, when molecule A comes close to another molecule, that delta positive end is going to pull the electron density of another molecule closer to it. And that then causes a different molecule to have a dipole. So we have the instantaneous dipole being formed because of the unsymmetrical movement of electrons. And this is in molecule A. Molecule A then comes close to molecule B, and this delta positive end of molecule A is going to attract the electrons within B, causing that to then have a delta negative end, and that causes it to then become unsymmetrical. So molecule A causes molecule B to also have an unsymmetrical electron density. And when this happens, we call it an induced dipole, meaning it is caused by another dipole. So to induce something means to cause something. So the dipole in molecule A induces a dipole in molecule B. Now, the induced dipole will always be favorably aligned with the instantaneous dipole. That means that of molecule A, so if this is A, and that is delta negative, the induced dipole that is in B will be delta positive. Or vice versa. If A is delta positive, then B would be delta negative. They will always align with each other. And these fluctuations will only happen very, very quickly and in small time frames. So this fluctuation of this electron density always moving creates dipoles very quickly and then causes the dipoles to stop. So we're getting this fluctuation and creation of dipoles, and the molecules are always moving. So when the molecules are always moving, regardless of how they move within your substance, they will continue to attract each other, because dipole A may be lost, that instantaneous dipole may be lost because my electrons go back to being symmetrical, but that doesn't mean that molecule C has not had an instantaneous dipole. So all the molecules within your substance will constantly be making instantaneous or induced dipoles. They would just be forming and reforming and forming and reforming each time. The more electrons there are in a molecule, the stronger the London forces. Okay, and we can see this trend when we look at the noble gases and when we look at the boiling temperatures, and we'll talk about how boiling temperatures are affected by intermolecular forces in topic 7b. So make sure to check out that video. So when we look at the boiling temperature of helium, in Kelvin, helium is 4.3. Now, as you go down the group, down to radon, you come up to 211 Kelvin. Now, of course, it is still a gas because room temperature is much higher than that, but you can see quite a large difference between helium down to radon, and it is because your electron density is increasing. The more electrons there are in a substance, the more likely they can fluctuate and they can become unsymmetrical. So therefore, the more electrons that are unsymmetrical, the larger that charge becomes, so the larger the instantaneous and the induced dipoles are. London forces can also depend on the size and the shape of the molecule. So the more points of contact that we have between molecules, the greater the overall London force. So if we were to draw out a skeletal formula of butane, what can happen is the molecules will align with each other like this. And you can see that we're getting points of contact all throughout the chain there. So we'll get points all throughout here on the chain length. And you'll be getting at these points of contact intermolecular forces. Now, if I take that molecule and I extend the chain length, you can see automatically I'm getting more and more points of contact. The more points of contact I have, the more London forces there are. because the electrons between the molecules are going to be interacting with each other. So the more points of contact, the greater the London force. Now, London forces are always present in molecules, regardless of whatever intermolecular forces there are, and that is because all molecules contain electrons. So if there are electrons present, London forces will exist, which is everything. So you can always use London forces as an answer if it asks you what intermolecular forces are within this molecule. You should always start with London forces and then look to see if you have the other two. So let's move on to the second type of intermolecular force. So let's look at the second type of intermolecular force, and this is known as a permanent dipole interaction. So just as a reminder about what a permanent dipole is, this is when we get a difference in electronegativity. Okay, and it has to be a fairly large difference in electronegativity. And that means that the difference is high enough that there is always a dipole present. So this time we are looking not at the movement of the electrons, we're looking at where they sit within the molecule. If you have a permanent dipole in a molecule, then it will interact with something else that will have a permanent dipole. And in an ideal world, they would be aligned correctly and there will be a favourable interaction. So for example, the delta positive end of this molecule, let's call this molecule A, is attracted to the delta negative end of molecule B. This is a favourable attraction. And so we're going to get some sort of intermolecular force here. Now, the problem with permanent dipoles is there are times where the dipoles are not aligned, and this is not going to produce a favourable reaction. So, for example, if I have the delta positive end of A coming close to the delta positive end of B, we're going to get a repulsion here. So we don't get that intermolecular force of attraction here. Now, because of that, when these interactions are averaged out, they are actually less significant than London forces between the molecules. So whilst they are stronger than London forces, they are less significant because they are not always favourable attractions. Sometimes we do get this repulsion happening. So we need to understand that, yes, whilst they are present, they actually don't have as much of an effect on its physical properties. It would be more likely to be London forces that would overrule the physical properties of a substance. So London forces and permanent dipoles are all to do with dipole-dipole interactions. We just have to remember what they are called. So if it is London forces, it is between our instantaneous and our induced dipoles. And if it's permanent, of course, they are between two permanent dipoles. So let's have a look at the third and strongest type of intermolecular force. These are known as hydrogen bonds. So in order for a hydrogen bond to exist, the hydrogen in a substance must be connected to a much more electronegative atom, and there are only 3 atoms that this can happen with, and it is when the hydrogen is connected to a fluorine, an oxygen, or a nitrogen. Now we can get intermolecular hydrogen bonding, but we can also get intramolecular, so this is within the molecule. However, we're not going to discuss that in this situation. We're only going to be looking at intermolecular forces, so hydrogen bonds between molecules. You'll discuss intramolecular hydrogen bonding later on in the A-level course. So if we look at oxygen, any compound that contains an OH group will form intermolecular hydrogen bonds. So that could be water, it could be an alcohol, or even a carboxylic acid. All of these will contain OH groups, so they're all able to make hydrogen bonds. So the one that we've got here is we can see water forming the hydrogen bond between the oxygen of one atom and the hydrogen of the other. So the oxygen is delta negative because it is the more electronegative substance, plus it also has a lone pair, and then we have our hydrogen bond shown by this dashed line here. And it is going to be attracted to the delta positive end of the molecule, and that is the hydrogen. Now, with water, there is some partial bond formation using the lone pair of electrons on the oxygen atom. So actually, it can form two hydrogen bonds with two other water molecules. Now, and a question that comes up quite a lot and is very important for you to know is that hydrogen bonds are directional and the bond angle is 180 degrees. So there will always be this linear 180 degrees angle here. That comes up quite a lot in multiple choice questions where it gives you a diagram and it asks for you to say, is this diagram correct or not? So just be aware of that. We can also get hydrogen bonding if a compound contains an NH group, because again, it's very electronegative. So an example would be in our amines, which you will go into more detail about in the organic topics in both AS and A2. But amines will have the the general formula of RNH2, so they contain this nitrogen connected to the hydrogens. Again, we have a lone pair here, and we have a delta negative being attracted to the hydrogen delta positive on another substance, and then we get this hydrogen bond forming here. Now, the only fluorine compound that has hydrogen bonds with intermolecular forces is hydrogen fluoride. Any other substance isn't going to have the hydrogen bond because fluorine has 7 outer electrons and hydrogen has 1. So as soon as they bond together, they are going to have completed the octet rule, so they don't bond to anything else. So hydrogen fluoride is the only example here. And you can see again, we've got this 180 degree bond forming here. And it is the delta negative of the fluorine being attracted of the delta positive of the hydrogen. So let's have a look at a past paper question on intermolecular forces. Now, typically these questions will link into the properties, but because we haven't covered these yet, I'll talk about them in a different video and you can see further past papers. What we're going to look at here is a typical 6-marker from a 2018 paper in January, and it is asking for all of the intermolecular forces between glucose molecules, and for each type of force indicating the atom that is involved. Now, the good thing here is we do not need to be able to explain the forces. You will see that in many questions about intermolecular forces, this sentence will be there. Unless they are specifically asking how the forces are formed, you do not need to give an explanation. So always look out for that. So we've got 6 marks here. So hopefully you can see that it's probably going to break down into 2, 2, and 2. So we're going to get 3 different types of intermolecular bonds. Now, earlier in the video, I told you that the first one that you should always have is your London forces. And it is because this molecule obviously has electrons. You can either say London forces or you can say instantaneous and induced dipole forces, but it's just much easier to say London. And these are going to be between or be caused by all the atoms in the molecule. Every single atom has electrons, so every single atom can have this fluctuation and can cause our different electron density, causing the dipole. Okay, if you look at the structure of glucose here, you can see that we have got some OH groups, we've got carbon bonded to oxygen groups. Now, because we've got oxygen here, we're going to get some differences in electronegativity. So we're going to see permanent dipole forces as well. Permanent dipole forces. And of course, we need to explain where we're going to have this. And it can be, there's two possible options. You can say it is between the carbon, which would be delta positive, and the oxygen, which is delta negative, or it could be between the hydrogen, which is delta positive, and the oxygen, which is delta negative. Either one of those would get you the answer. You can also say between carbon-oxygen bonds, between polar bonds, or between oxygen-hydrogen bonds. However you want to phrase that would be acceptable. And then the last one is, of course, our hydrogen bonds. And then we have to explain where these arise from, and this is the way that we have to discuss this is we have to say that we have got these bonds forming between the hydrogen of the OH group and another oxygen. So we have to be very specific about what atoms are actually taking part here. We could also say between the OH groups, that is also an accepted answer, or because hydrogen is bonded to a very electronegative element, that would also be an accepted answer. So you get 1 mark for each of the naming of the forces, and then 1 mark for each of the atoms that they are between. And you can see there that we've got the mark scheme for this, so if you were trying this question yourself, you can have a look at the answer. That's everything for how intermolecular forces are formed. As I said, this does lead on to the next video, which is topic 7b in the physical properties. So please make sure to check that out. If you do have any questions, feel free to leave a comment below, and we hope to see you back on the channel for future revision.